Twitch. Okay. So you should... Okay, is it live now? It is. Okay, it should be live. Okay, great. I'm just doing this because it's easier, because YouTube is going to have this, so it's just going to be easier to do this. Okay. Okay. So let's just talk a little bit about string formatting, I guess. So what is string formatting? So we just covered input and output, right? Oops, something opened up here that I didn't want to. Okay. And now it's time to go into string formatting, which is really, really important, and I already covered part of it, but not really formally in a way. So string formatting is when we do, for example, something like this. So we have a equals 4, doesn't matter. Now we're going to print, and we can always do something like and we can format and say a. And when we run this, where is it? Where is it? It's here. We're going to get A's 4. What we just did is we took a normal print statement, and every time we want to specify a particular variable or an expression, we use these curly braces on it. So we can have these curly braces here, we can have multiple curly braces, and then what we can do is we can do, after the quotation mark, so applying this to the string, this is the string, applying this to the string, dot format, and then use, because it's going to be kind of like a function, it's a method. Oh, what's up? Yeah. So we can just format this, and we can include in order as they appear our variables. So in this way we can actually do a. We have three actually we can do we can do expressions in here. So we can do a times 2 and a plus 3. Now when we run this, it's going to give us a is 4 and then comma 8, 7, whatever, right? Now you can also put numbers in here, so 0, 1, 0, 2, and 1. And you'll notice that now these switched because the numbers being put in here... Hello, how are you doing? The numbers being put in here are the order in which they will appear. So this is the order number 0, this is order number 2, so it's going to be, and this is order number 1, so this one's going to go first, this one's going to go next, this one's going to go afterwards, and still the order in which you specify them are the order in which you wrote them. Right? So, easy enough. Now, if we go into Google somewhere and we also put string formatting Python, you can get this really easily. Oh, okay. I guess this works. Maybe I don't know about this one. Oh, yeah. Don't study this. This is pretty old style. Also, what I've just showed you is not the best way to format it, but yeah, here it is. For example, this is not what I wanted particularly to do, but you can gather all this info really easily on the internet as well. But here's what I wanted to introduce to you as well. This is a pretty standard approach, but it's kind of bulky. What can you do to make it better? Yeah, of course, you can also put like a name in here. You can say name equals 3, right? And then you have to put them, again, it's just a bit too bulky for me. So what I like doing is using an F formatted string, which is what people should be using, to be fair, in my opinion. Which is the same thing, but just a very compact version. So we use an F. So remember how if we want to define a normal string, we just use quotations. If we wanted to define a byte string, we use a B. And this in here is bytes. If you want to define a raw string, it's an R. There are more. Now, an F formatted string, it's an F. And what this allows you to do is it allows you to do the same thing with the curly braces, but you don't have to do the format. You can just type in the expression you want inside of here. So you can say A, just right there. You can say A, you can say A plus 4. So A, this is A, period. Now it is, and then you can put A plus 4 or 8 times 4, doesn't matter, whatever you want. And when you run this, you're going to have the same output as before, but you don't need to do the format. It's just pretty clean, easy to understand. And I think this is really the best way. What you can also do as of Python 3.8 is you can do an equal sign after any expression. After just before the curly ends, you can just do an equal sign. And what this does is it's useful for debugging, because when you run this, it's going to print the whole expression inside of it. So for example, this is A equals 4, instead of just saying 4. Now it is 8 times 4 equals 16. Like, it will print the entire expression. It will evaluate it correctly, but it will also print the expression. And this allows you to debug code. So let's say your print statements or whatever is not giving you the correct results that you want. You might want to put some equal signs there and see if the expression is being correctly evaluated, or what's wrong with the expression. So it's good for debugging. But yeah, there are little quirks about it. So these are this is the basic of string formatting. Now, you can also do, let's see if I can pull it up. Where is this? Damn it. It's supposed to be pretty simple to search the documentation for this, but let's do this perhaps. Oh, there we go. Here we are. Here we are. Oh, I'm not showing it in here. Sorry, I should have been doing it here. Okay, there we go. So if you just go for string documentation, you can get a lot of value from this, of course. But what I want to, and again, you're going to get to formatting and all of that stuff. But there we go. This is kind of what I wanted to also talk about. It's pretty, there's a lot in here. There's a lot in here. And you can definitely go through it if you want to. I'm just going to give you the most important aspects of this, and then you can go deeper into if you want to or not. So you can format numbers inside of print statements as well. And how would you do this? Oh, hello, Dragonsh. What's up? Oh, thank you. I'm really glad that it has been helpful. So what does this mean? So if we have A equals 5 and B equals 4, and you print, let's use a formatted string, you print A divided by B. Now, notice that we don't put text in here. You can, but since we don't put text in here, there's no need for a formatted string, because we can just say print A divided by B, right? But it becomes useful if you want to have, text. So the result is this, or whatever. So now let's do this, and what's going to print is 1.25. Okay, that's good enough. Now, let's say I want 1/3. The result's going to be 0.333. But here's the thing, what if you want to format this further and make it so that it only outputs the first 2 digits? How do you do this? Well, this is why this is going to be important. You can format these further And so right here, for example, it's actually a bit confusing in this particular example, but you can use your what is this called? It's a colon with the specifier for how many digits and decimal digits to allow. So, for example, where is our? Is there? I wish there was a table. This is actually really confusing. I'm sorry. I always recommend going for the documentation, but this is actually quite confusing. Like I get what they're saying, but there's no clear way for people to get a complete wait. Let's put number formatting. Python table, I guess. Cookbook? Oh yeah, this is more useful, for example. If you Google this, it's more useful for you. It's kind of like a little table of the kind of ways in which you can format particular things. So let's say that, so right here, so the colon dot to f, it's going to format float 2 decimal places. So this is kind of what we want, right? So we can do, oops, where is the, there we go. So we can do this, and now the result is 0.23. Right, and now here's the thing. If we do 1, for example, in here, nothing changes. If we do 2, obviously, nothing changes either. And where is it? Yeah, here. So you can use these numbers to left align them, to right align them, to also pad the numbers with a particular thing. So it's really useful. And well, what I demonstrated before, wait, where is it? Here. So let's go for a different example. So let's go for, let's say, we're going 4 divided by 2 or whatever, right? And let's pick up this thing here. Yeah, there are. It's pretty confusing. And this is much better. I'm liking this. I'm finding some trouble with the particular, what do I say, examples that I want to give, because I need to think of numbers that make sense using particular examples, which is going to be difficult, I guess, out of the blue. But I'm looking at their examples, and they're actually pretty decent, right? So that's why I kind of want to go along this particular line. So as you can see, you can do a lot of different things. And if you go with this example, you notice how you're padding this with zeros, with the width of 2, right? You can increase this width to be like 4, and then you'll have 3 zeros and a 5, similar to this, right? And there's so many things that you can do in here that I cannot cover it all, right, obviously, and you can just get what you need. The most important things to realize is, if you want to limit this to 2 decimal places, you can do this. If you want to, you can do more, of course. And another important thing might be this right here, which is where you can use the sign. So right here, instead, oops, you can use a sign, and you'll have your positive number, or of course, if this was a negative number, you'll have your negative number, right? And I guess this can be useful for many situations as well. You can use for comma-separated values, for percentage, all sorts of things. Okay, but that's string formatting in numbers in a way. It's still string formatting, right? And I guess this documentation is actually pretty good. It's good. It's going through the old way of formatting, then the new way of formatting, and then it's not actually using the F-formatted string that would be pretty useful. Because look, here's the thing. For example, this. Let's take this example from this guy. Is this more or less readable than simply? Actually, let me let me just copy this again. Let's do this. Okay, now let's do an A, let's do a B, let's do a C, let's do a D, let's do an E, let's do an, oops, A, B, C, D, wait, did I mess it up? Oh no, there was one more, right? Was there? Yeah, doesn't matter. It does, but let's just assume that we'd have an additional one here, right? Just for the purpose of showing you that one will be simpler than the other. So, which one is more readable? Now, to be okay. So, which one is more readable, the first one or the second one, right? And that's my whole point. So, this would be like the way to do it, but of course, well, the modern way to do it would be with F formatted strings. I call it F formatted strings, but it's just like F strings. It's just going to be way more readable. So that's why I'm showing you this. Thank you for the follow. Really appreciate it. But yeah, and you can read the documentations on this. It's pretty simple, self-explanatory. So string formatted is not very. It's a pretty simple topic. If it's a pretty low density topic, and I have no clue where I put my vape, which is a problem. Anyway, so yeah, so this is string formatting. So let's put a little plus here. Oh, thank you for the host. Really appreciate it. The troubleshooting is something you do not see in edited montage videos. Yeah, and that's really, I thank you for that. And I think that's really important. We don't see, like, all the videos that I've ever seen about programming or anything similar. You never see people actually going through that debugging process. Maybe if there is an error that is incredibly common and it's posted in comments, people might do it. But you never see people actually just sitting down and doing things actually live. Because if that happens, then you're going to also see the process of getting errors and how to solve them as well. And that's really important because I don't know, a lot of people seem to have the idea that when they watch videos, all the code is perfect, right? And they just write the code like in perfection and it just runs and it's perfect because it's scripted. And people, you know, think that they cannot do that ever because, you know, I always make errors, like there are always errors, and you know I cannot get to that level yet. But that's the thing, that level is unrealistic. Of course, with simple things it happens, but there are always going to be some troubleshooting being done, even in simple things, because you know people are human. And I guess it's important to know, like, and to kind of showcase the way in which the way in which at least I tend to solve some of the problems, so that maybe you can take some of that and solve problems yourself. So I think that's pretty important too. And thank you for that remark. But yeah, that's a string formatting. We're going to go into basis and virtual environments in just 1 second. I would love to split this into two, but I don't want to like turn my stream and turn it on again. So I'm just going to start right now into basis. So just a little recap. Right now, today we've learned basic I/O, so how to interact with files, reading and writing, so reading from files, writing to files. We also learned how to do these I/O operations on in-memory buffers, so without dealing with files. When we'll be doing assembly, we're really happy for assembly. We will do this, so after I do the Python, we're going to go into C. And as we go into C, I'm going to introduce some assembly as well. And then we're going to get really into the assembly. It's going to be really interesting. So yeah, so the basic I/O is learned. String formatting, so basically how to deal with strings, how to represent strings and represent expressions and variables inside of those strings. We've learned that too. Now we're going into basis. And why is this important? What are bases? And this is actually where I'm going to probably full screen this. because I think I have to start, because it's just simpler to draw diagrams and stuff. So, okay, this is really not comfortable. Okay, so what's a base system? Or what's a numerical base system? Every time we count something, we usually use base 10, right? So let's start with base 10. And what does that mean? Well, base 10 is a numerical system where where it is consisted of 10 digits, right? That's why it's called base 10. There are only 10 base digits, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? These are the base digits. That's why it's called base 10, because there are 10 of them. Now, when you count, you go from 0 to 1, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9, you go to 10, right? 10 is not a digit anymore. 10 is composed by two digits, the digit 1 and the digit 0, right? And that's why it's not a base digit. And this is really how you count, right? And why do you go to 10? So let's look at it in a different way. So you have, again, 1, you have 2, you have 3, you have 4. Let's continue here. You have 5, 6, 7, 8. Let's continue here. You have 9. And then when you get to 10, what you're really doing is you're putting a 0 here, and you're saying this is 9, this is 0, 9, because it's the same thing. It's actually what you're doing, right? You just don't write the 0 because it doesn't matter. And now that we have no numbers on this side, because after 9 there's nothing again, this goes into 0, because after 9 there's 0. So you loop around, this becomes 0, and of course this has to be incremented. Oops. So this becomes 10, right? Oops, so 9, 10. Now afterwards, so 11, 12 again, we're always incrementing this number until of course we get to 19. Now when we increment this number, there's no digit after this, so it goes back around into 0. So this becomes 0, and of course we have to still increment this one, so this becomes 20, 21, etc. until we go to until we go to 99. Right? Now, if we increment this one, it becomes 0. If we increment this one, it becomes 0. But don't forget, the 99 is 0, 99, right? So when we increment this one, it becomes 1. So this is 100. So then 101, etc. And this is how we count. Right? I guess people understand how we count. Now, this can be applied in any base. So we just happen to count in base 10 normally, because that's what we started doing. We defined the 10 digits, but we can do this in any base. So let's pretend that we're now in base 4, right? So what is base 4? So hello, hey Elementa, how you doing, man? How are you doing? We didn't cover that much. We actually did cover quite a bit. I was just explaining base 10. So we're going into bases. I'm good, thank you. Oh, that's awesome. But yeah, just for some context, I was just explaining base 10, so how we count in it, right? So we have 0 through 10, and 0 through 9. And as we go into 10, right, we start reusing the digits that we used before and always incrementing them, right? And it's the same thing when we go into base 4, any kind of base actually. So what are the digits of base 4? Base 4, as the name suggests, has 4 digits, right? 4 basic digits. So it has 0, 1, 2, and 3. These are 4 digits. This makes up base 4. So how do you count in base 4? Well, let's start with 0, then 1, then 2, then 3, and there is no 4, right? Because the digits of base 4 is from 0 to 3, so there is no 4. So when we get into here, and we increment 3, it goes back around, right, into 0. But again, remember that this is the same thing as saying 0, 3, right? So this is what we're doing, and we're still incrementing this one. So now it becomes 10, right? And then let's continue here, 11, 12, 13, and then we cannot increment this further to be 4 because there is no 4. So when we increment this, it becomes 0. And when we increment this, it becomes 2. All right? Then 21. Wait, I actually erased it. I didn't mean to erase it because obviously it's the continuation. So 22, again, 23. There's no 24 because it just goes into 0. 2 goes into 3. So it becomes 30, 31, 32, 33. And now we reach another problem, right? If we increment this one, it's 0. If we increment this one, it's 0. But again, don't forget that you have a 0 here, right? So when you increment this, it's 1. So this becomes 100. So this is like how you count in base 4, right? And it's the same concept as base 10, except you're limiting your digits to 0 through to 0 through damn it. You're limiting your digits through to 0 through 3. Right, and you're doing so your digits will always be so you have a base 4. Your digits are always going to be mod 4, right? So what this means is you start with 0, then you go to 1, then 2, then 3, and then you go back into 0, and then 1, and then 2, and then 3. You go back into 0, 1, 2, 3, right? And that's why we've been, you know, when you reach say 13, this 3 goes into 0, right? And this 1 goes into 2. And once you get to 33, these 2 go into 0, and then this other number goes into 1. So this is how we count. Now, why is this useful at all? Why not just do everything in base 10? Well, it's useful because we can do mathematics with it. And we can also do it in base 10. It's just, it becomes harder depending on what environment we're in. So for example, let's do, so let's say we're in base 4, right? Base 4. And also, okay, let me do something else, which is going to become a bit clearer. When you have a number like 1010, do you guys have merge? Yeah, we do. Let me just show you really quickly. So if you go into, there we go. So whitehathacking.tech, we have a little merge link. We have a really cool merge. We have more merge coming out as well. Okay, a little side note. Sorry. Okay, again. So let's say we have a number, and this number is 1010, right? 1010. And this number is base 10. What does this mean? You might have learned in high school that you can separate the different units of the different digits of a particular number into certain places. So for example, this, wait, let me do this larger. So 1, 0, 0, 1010. You probably learned that this can be separated into, let's say this is the ones, this is the tens, this is the hundreds, and this is the thousands, right? Are you guys familiar with this? You probably learned this in high school. So you have the ones, the tens, the hundreds, and the thousands. And this makes sense, right? Because obviously this is the ones. Yeah, it makes sense. Why? And why is it called this? And what are we doing? What does this mean? Well, this actually has a very particular meaning, and there's a very specific reason why these are called the ones, the tens, the hundreds, the thousands. And this is because what you're really doing when you are representing a number in any base, in any base, it just happens that this is base 10. What you're doing is you're taking that base and you're saying, well, this first digit is our base raised to the power of 0 times that. The second digit is 10 raised to the power of 1, 10 raised to the power of 2, 10 raised to the power of 3, etc. Right? If you had a larger digit, a larger number, you would do this for larger. You would continue, right? So you start at the left side, you go into right. You start at the right side, you go into the left side. You start with 0, and then you just increment it. And what this number means, what 1010 means, it means the result of multiplying 1 times 10 to the power of 3 plus 0 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 0 times 10 to the power of 0. Right? And the reason why this becomes the ones, the tens, the thousands, the etc., the hundreds and the thousands, etc., is because, well, what is 10 to the power of 0? 10 to the power of 0 equals 1. 10 to the power of 1 equals 10. 10 to the power of 2 is equals 100. 10 to the power of 3 equals 1,000, right? So that's what you're doing. So this is the ones, because you're multiplying by 1. This is the, so this is the ones because you're multiplying by 10 to the power of 0, which is 1. This is the tens, you're multiplying by 10 to the power of 1, which is 10. Again, hundreds, thousands, etc. And the result of this is your number. So 1 times 10 to the power of 3 is 1,000, so this is 1,000. Plus, well, 0 times any number is 0, so plus 0, plus 1 times 10 to the power of 1, which is 10, plus, again, 0 times something, 0. So this equals 1010. So this is your number, right? And this is the same thing in any base, except the difference is, instead of having 10 here, you have your base. So let me, I can clear it better like this. So let's say we have, again, let's say we have base 4, right? And you have the number 200. So what you're doing is you're doing 4 to the power of 0 here, 4 to the power of 1, 4 to the power of 2. So instead of calling it the ones, the tens, the hundreds, what you're going to actually call this is you're going to call it, well, technically you should call it, the ones, you call it the 4s, you call it 16s, right? Because these are the results of these numbers. So now if we do this multiplication and add this together, we're going to get us 2 times 16 plus 0 times 4 plus 0 times, right? Which is going to be 32. So the number 200 is the representation of 32. And how can we actually see this? Well, we can count it, right? So it might take a while because 32, but let's we know it requires 3 digits, so let's start with 0. So this is 0, and I'm going to erase it, but every time I erase it, I'm going to make it obvious, I believe. So 0. This is 0. You know what? Let's just do it in a different way. So 0, 0, 0. This is 0, right? 1. This is 1. 2. This is 2. 3. This is 3. 0. Again, remember. So when we increase this, of course, it's going to go into 0. So now we have to increase the next one. So 1. So it's going to be 4. And this is the representation in decimal, right? We're just counting it in decimal, and this is base 4. So 0, 1, 1 would be 5. 0, 1, 2 would be 6. 0, 1, 3 would be 7. I hope I'm not making any mistakes right now, but then 0, 20 would be 8. Then 0, 21, 9, 22, 10, 23, 11, 30, 12, etc. And then and you would continue this until you get to 200. It's going to take a while, and 200 would be 32. Now I can do this with a lower number just so you can get it. So we know that 30 is 12, right? For example, we just realized that 30 is 12. So let's stop here and let's deal with this 30. So we know that 30 in base 4 is 12. So what are we doing when we're doing base 4? So 30, we have our 4 to the power of 0, 4 to the power of 1. Oh, this is actually wrong. It's not. I'm an idiot. Am I? No, it is. Oh, wow. I just brain farted. First of all, so again, we're multiplying these. So 3 times 4 to the power of 1, which is 12, plus 0 times 4 to the power of 0, which equals 12. So we can see that this is 12. Which number that ends with 4 is 0? Yes, this is what I was trying to say before. It might be a little bit of a difficult concept to get at first, but here's the idea, right? So your numbering system starts with digits, right? This is your entire known. And oops, this is not showing anymore. Why is it not showing anymore? Oh, it's lagging. Okay, this should, okay, it's lagging, but it's back now, I think. Okay, so why is this, okay, so this is base 4, right? Your whole known world are these 3 digits, are these 4 digits. So to compose numbers, you start with the lowest of them all. So you start with 0. Then to increase this, you start, you add, so it goes into 1, and it goes into 2, and it goes into 3. Now, and here's the thing, these are the only digits that you know. When you start after 3, the next digit is not a base digit, so you have to combine digits. And which digits do you combine with? Well, if you want the next lowest number, you have to combine it with the next lowest digit. Of course, the next lowest digit after 3 is 0, right? Now, of course, if you just put 0, you're back where you started. So you have to add something to the left of it. And if you remember, 3 is the same thing as 0, 3, right? Which is what you're representing. So the lowest number after 3 is 0, but the lowest number after 0 is 1. So that's why you go into 10 here, right? It's a modular, it's a mod operation. So you're going into here and then you're going back down. And here you're going to here and you're going back down, right? So 3 is your limiter. Anything after 3 goes into 0. Yeah, it's a way of counting. Yeah, it's just the way you count, right? It's the way you represent it, because 10 here is obviously the lowest number after 3, right? Because 4 does not exist, right? So this would have to be 0. And if you do, for example, 13, right, that's going to be after 10. So 10 is the lowest number after 3. That's the idea. So, and yeah, so if you're, and this is how you represent, next would be 11, 12, 13, then 20. Yeah, exactly. So 11, 12, 13, and then of course 20. Like this, the 3, of course, the next one would be 0, and then we have 20. Right, and it's the same thing as if, as soon as you go into, well, there's no 9, right? But if you go into 33, well, you're 33, the next would be 100, right? It's the same idea, the same concept. And you do this in any base. This is base 4, but you can do this in base 2, base 3, whatever you want. No problem. And why is this important? Well, because you can do mathematics with it, right? So let's say 12 times 2. This is 24, right? 12 times 2 is 24. Well, and this is a fact. 12 times 2 is 24. Let's look at what 12, so let's look at base 4, right? So let's say that this is in base 4. We're doing this in base 4. What is 12 in base 4? Well, we'll just learn how to look that up. So 12, we're going to have our exponents. So we're going to have 4 to the 0, 4 to the 1. And this is going to be equal to 1 times 4 to the 1 plus 2 times 4 to the 0, which is going to be 4 plus 2, which is going to be 6, right? So this is 6. So we know that this is 6. Assuming I didn't do any stupid mistakes, this should be 6, right? And then 2, in base 4, 2 is just 2, right? Because if you do the 2 number, right, 2, and then you use your exponent, right, so you do your 4 to the power of 0, all you're going to get here is going to be 2 times 4 to the power of 0, which is 1, so it's 2. So 2 is just 2. So 6 times 2 equals 12 in decimal. Right? Now, if you do the same thing with 24, where you figure out what this is in decimal, right? So you have your 4 to the 0, your 4 to the 1, and then you look at this, and so 4 to the 1 is 4, so 2 times 4 plus 4 times 1, so that's 4, which is 12. So at this point, you realize that it's the same thing, right? So 12 times 2 equals 24 in base 4, right? But 12 times 2 also equals a 24, well, 6 times 2 equals 12, in this case in decimal. You can, obviously, the mathematical relationship, like the mathematics is preserved, right? You can do mathematics in all kinds of bases, and the answer is the same across all bases. You just have to convert the numbers to those bases. And this becomes really, really useful, because when you're dealing with systems of information or systems where you're dealing with let's say binary states, or yeah, let's go into electronics. It's good for base 16 notation. Oh, base 16. Okay, let's talk a little bit about base 16. Base 16 is pretty useful too, and this is something I should have talked to before as well, because for base 2 or base 3, you can use the digits that we normally know. But for base 16, so we have 0 through 9, right? And after 9, you cannot use 10, because this is 2 digits, right? So we have to come up with different digits, because it has to have 16 digits, right? So then we come up with A, we come up with B, come up with C, come up with D, E, and F, right? And again, 0 through 9 makes 10, so 0 through 9 is 10, 11, 12, 13, 14, 15, 16. And this is 16 digits in total. Hey, Neox, what's up? Yeah, for assembly, right? For a lot of purposes, not just assembly. But I'll get to it. Now, why is this important? Well, why is base 16 even used? Well, working different bases is really useful, depending on the environment that you're in the system, in the world that you're in. Let's say that you are working with binary data, right? You're working with binary data. So let's just go into that. So you have electronic components, right? So we talked about this before in the very beginning, but it doesn't really matter too much right now. But the idea, oops, I forgot the light bulb. It does, let's put a light bulb here. So this is a little light bulb. It's connected to this. And this is a switch, okay? And you don't really need to know anything about this. Let's just pretend like this is just power. If you don't know anything about circuits, this is just the power. This is electricity going through, right? And this is a switch. What this means is, right now it's disconnected. So, you see these are basically, think of it as cables of electricity, right? But this is not connected, right? So electricity does not flow from here. It does not flow to there, because it's not connected. But when you push the button, it becomes closed. And then it connects. And as it becomes closed, electricity passes through here. So that's what a switch is, right? So first, it's when the light is off, the switch is open. So electricity, is coming, and it's actually not passing here. So it never reaches the light bulb, right? Even if you consider the electricity comes through here, it never closes the circuit, right? So if it never closes the circuit, the light bulb will never light up. But when you click on the switch, this will close, right? And suddenly you have light on the light bulb. Okay? Pretty simple idea here. and that's it. The signal that you get from this is either it's closed or it's open, right? It's either closed or it's either open. So it's either 1 or it's either 0, right? Either the electricity passes through it or it does not. And this is a binary system. If you gather information like this, it's a binary system because the only answers are 1 or 0. Right? They're in a different color. Red seems a bit weird. So it's either 1 or it's 0. And this is why binary comes in handy a lot, because you can do mathematics with it. So let's say the number 10. For the light bulb on the circuits, I think it's a circle with a wave inside. Oh yeah, that's the way you should represent it. That is true. But yeah, I just tried to actually draw a little light bulb, but I'm pretty bad at this. But yeah, so let's think about the number 10. And right now we're in base 2, by the way. So 10 times 10, of course, is going to be 100. Right, we know this. And 10 times 10 is also 100 in binary, right? And this is why it's really important. Because or X inside a circle. Oh, I guess, yeah. Okay, makes sense. Because it allows you to deal with a universe that only has 2 digits, or only has 2 different states, in case of base 2. If you have something with 3 different states, maybe a ternary system is more useful. Because it allows you to just perform operations with numbers that make more sense in that particular environment, in that particular system that has those characteristics. So in this case of binary, our input, our data is going to be either 1 or 0, and it makes sense to make operations considering that duality of data, that it's binary. It's a binary system. Oops. If we had to do this in a decimal system, by the way, it would start becoming a bit more. It would start making a bit less sense in a lot of the situations because, for example, I don't know. Wait, let me think about this. So let's say you have this is actually a bit. It's difficult to think of a good example right now, but I'll do it. So just a normal. I don't want to talk a lot about memory because you guys because we haven't introduced it yet. But let's see. Okay, fine. So let's look at data. So binary data, right? So binary data is 1s and 0s, so it's base 2. So in base 2, the only digits are 0 and 1, right? Two digits. And we have, say, 2 bits of data. Right? This is 2 bits of data. By the way, what is a bit? A bit is just shorthand for binary digit, right? So in this case, we have 2 bits of data, 1 and 0. And these were the inputs of a particular thing that we did. Or sorry, the outputs of something. And this output is from let's say that this output is from an addition of 2 different outputs. So you have an output that gave us 1. You have another output that gave us 1. And we summed this together. And this ended up giving us 10. Because 1 plus 1 equals 10. Right? In binary. When you receive this 10 output, if you want to make further calculations with this or further manipulations, if you're doing it all in base 10, well, first of all, you already did a binary addition here, right? If you treat this as 2 instead of 10, you cannot, of course, you can't use 2 as an input for whatever other thing you're having. Because remember, if things take if things output binary data, they take input. They take binary data as inputs too, right? Electronic systems. So, and the binary data that they take as input as electronic systems is either the electricity passes there or it doesn't, right? So that there's no way to input a 2 in this sort of thinking. So you'd have to convert this into something that is the same thing as 2, which is going to be 10 in binary. So it becomes pretty hard to do this. And that's why these, for example, the binary numbering system is really important and really useful for binary calculations, which is all the computers are really doing. So, so this is important. Now, again, for binary and counting in binary, it's just as easy as the rest. I'm just going to show you now because binary is pretty important, right? So you start with 0 again, right? 0, 1. There is no 0, 2, so this is 1, 0. Should have, yeah, 1, 0. 1, 1. And there's no 2, right? So this just becomes 100, right? Right? It's the same thing. Now, what really is important here is to realize that we have different bases for different purposes. And they're pretty useful, and it's important to understand what they are, right? So again, if we have 1011, right, this is actually going to be 11 in decimal. But how do we prove this? Well, again, we start with our base to the power of 0, base to the power of 1, base to the power of 2, base to the power of 3, and now we just perform the normal addition and we add it. The multiplication and we add it. So 2 to the power of 3 times 1 plus 2 to the power of 2 times 0 plus 2 to the power of 1 times 1 plus 2 to the power of 0 times 1. Right? Now, 2 to the power of 3 times 1 is 8. 2 to the power of 2, well, times 0, this is just 0. 2 to the power of 1 times 1 is 2. 2 to the power of 0 plus 1 is 2. This is wrong. It's 2 to the power of 0 times 1, which is 1. So 8, 10, 11, right? And this, of course, in base 10. And we can represent bases of numbers by doing a little subscript. So you can say, for example, you don't see it very often because it's really not done very often. There are very rare occasions where you actually need to show this because you are either working with one base or the other. But you can do this, and 2 is the same thing as 11 and 10. These are the bases. Okay, so we understand bases a little bit. I need to go work. Have a great afternoon. Thank you, man. You too. Have fun at work. Off topic, do you know a way to make money passively online? Yeah, I really don't. I mean, you have ads, you have surveys, you have all sorts of stuff, but good money online only if you actually open up a company or something, I think. I'm not entirely sure. I'm not the best person to ask for that, honestly. So yeah, so we took a look at bases. Now in base 60, by the way, right? So these are other applications. So we use time in base 60 because we consider that after, when we say time, I mean when we're dealing with the seconds, right? And so after 59 seconds, this becomes 1 minute, right? And again, so, and then 1 minute, blah, blah. So 1 minute, 25 seconds, 26, 27, until you get to 59. And suddenly you're at 2 minutes, right? And as soon as you get to 59 minutes and 59 seconds, the next step is 1 hour. So you see how this is the same thing as what we've been doing for base 10 or for base 4 or for base 2. Right? The same concept, right? Except for base 60, you have 60 digits from 0 to 60. Once you pass that, you have to start using you have to, start the count again. So after 59, it goes 0. Now, in base 60, we actually represent things with these numbers. So it's a bit different because 59, you can consider it as a digit. But yeah, we do that. We work with other bases as well. But the most important thing to keep in mind is base 2, base 16, base 10. These exist and are pretty common in our day-to-day lives. Especially if you're a programmer, if you want to go into reverse engineering, you're going to deal with base 2 and base 16 more. Now, why is base 16 helpful? Well, it's kind of a little side note, but let's talk about what a byte is. A byte, if you look up in the definition, right, a byte is 8 bits. And what are bits? Well, a bit is a binary digit, right? Base 2 digit, so it's either 0 or 1. So it's 8 digits of either 0 or 1, right? So you can think of a byte as going from 0, 0, so 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 8 zeros into 8 ones. Right? This is the whole range of a byte. A byte can have 256 different values. Why 256? Well, because this is 256. And how do you prove it? Well, let's figure out what 1, 1. So what 8 ones in base 2 really is. So if we're doing base 2, again, this is 2 to the power of 0. I'm just going to write the number that it is instead of the power. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 32, 64, 128. Right? Now the result of this is going to be, of course, it's 1 times everything, so I'm not going to write the 1 times. So it's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, right? Now, so if we do this, so 2 plus 1 equals 3, 7, so 15, 16 is 31, 31 plus 32, so 63, 64 plus 63, 127, so this is 128 plus 127, just 255, right? So we know that this is 255 in decimal, and it starts at 0. So it's 0 through 255, which is 256 values, right? So a byte has 256 possible values, right? Great. Now, this means that there are 256 different ways in which you can represent a byte. And if you have to write it in bits, it's going to be really, really difficult for you if you're doing this. Why? Well, because let's say you need to represent 20 bytes, and there's you need to work with 20 bytes, and you need to let's say you're looking at a file that has binary data, and you need to kind of parse through it and figure out some patterns in it, and it just has, let's say, 60 bytes. Okay, 60 bytes, not a lot. But now 60 bytes is not a lot. But when you consider that each byte is 8 bits, right? You certainly have, which what you have a very large number of do this, especially when we get it to, we're not necessarily complicated, but pretty long to actually represent it like this. So how can we represent it in a more compact way? What the hell? Square mirroring? There we go. How can we represent it in a more compact way? Well, we can use other bases to represent those numbers. And so if, let's talk about base 10. We could use base 10 to represent the binary digit, to represent bytes. But there's a problem with using base 10 to represent bytes. So if you look at there are some kinds of calculations it's just not possible for you to do in your mind. Let's call up a calculator here. Some are just impossible, right? Oh, oops. Okay. So, the number 255. So, one way that you could represent this, right, in decimal, right, is you can assign a number to it, right, and then you have less. So zero would be, zero would just be, 0. 1 would just be 1, right? And then as soon as you got into 10, for example, this would be 2, easy enough. And when you get to 1, 1, 1, 1, 1, 1, this, which is 256, you just represent it as 256, right? And this is fine. It's perfectly fine. But it's kind of a problem because you it's a problem because you don't get how do I say this? Let's look at it from the other perspective. So I mean, it is a problem because it's actually way more complex to work with than base 16, but it's not a problem because we can't do it. So if we look at base 16, we realize it's simpler to work with this, and it's better in a way. So base 16 makes it so that you can represent a sequence of 8 bits, any 8 bits, using at most only 2 digits. This is really important. So 0, 0 is 0. FF is going to be the last, so it's going to give you the, so if you, okay, let's do this in the way that we were supposed to. So, because doing math with this is not entirely, how do I say this, is not entirely, oh god, it's not really automatic. So let's count with this ourselves. So I'd never counted with letters before with you guys here, so this is why I think would be better to do it with the letters. So we know what happens up until 0, 9, but then we don't go into, actually we go into the other digits, but 10 happens much later, right? This is the difference at base 16 because we haven't reached all the numbers. Remember, this is goes, so 0, 9, then AF. So from here you still have 0A, you have 0B, you have 0C, you have 0D, and then you have 0E, and then you have 0F, right? And if you look at this, of course, 0F is going to be the last number, so this starts at 2, at 0. And I didn't write the other numbers, of course, but this will end up at 15, right? Oh, you can't see this. I'm an idiot. This will end up at 15, right? So after this is where you go into your 10, and you're going to your 11, etc. And you repeat the same pattern over and over again. So and also let me show you something that you might not know, because it also, if you want to mess around with values and stuff, it's way easier to also just go into Python and try to terminal, and you can actually represent hexadecimal by saying 0x, let's say FF, which of course is going to be 255, or 0x 0e for something like that, or same thing. You can represent this. You can also represent binary numbers, so 10 in binary. So you use 0 and then x for hexadecimal, and then b for binary. You just put, or you can do int and also represent this. So let's say FF in base 16. It's the same thing. But yeah, this is just the idea that I wanted to put to give you. Going to be from 0 to FF, right? Because FF is going to be 255, and there are only 256 possible values for a byte. Great. So this means that you can represent any single byte using 2 digits. This is huge, because it allows things to be incredibly compact, and the mathematics just flows normally as it always has. And it becomes incredibly useful. It becomes incredibly useful, especially when you have, for example, things like this. So you have, right, when you have like things like this, or any sequence that has a lot of that it's not just 1 byte, right? We're talking about many bytes. So we're talking about 4 bytes. We're talking about 6 bytes. We start getting big numbers, and if we were to do this in decimal, we would have huge numbers that we couldn't really work through very well. But with hexadecimal, things are pretty neat and tidy, right? Because you can equate 4 bytes for 4 bits for half of this. So you can always understand this as a byte, understand this, right? So it just becomes easier. And I can prove it to you as well. So the proof for this is really interesting. I mean, how would I prove it? There are plenty of ways to prove this. It's a bit of a side note, but okay, let's go with this. Right? What is this? This is 1,000. What is this? This is 100. What is this? This is 10. This is 1. Okay. So how many digits does this have? 1. How many digits does this have? 2. How many digits? 3. How many digits? 4. If you notice a pattern here, you'll notice that between these two, so between 10 to the 0 and 10 to the 1, the value, so the value that you need to raise 10 to the power of to give a number that only has 1 digit is going to be between 0 and 1, excluding the 1, right? Because 10 to the power, if you're considering whole numbers, we're just considering whole numbers, right? So 10 to the power of 0.999. So if we make this with our brilliant calculator here, so it's 10. So let's go 10. Where's the power thing? I just downloaded this. I've never used this particular calculator, so I still need to find the symbols for it. So, and I can't actually see this properly, but wait. Where on earth is it? Is it not here? Okay, let's just do this. 1 times 10 to the power of 0.99999, right? This is going to give you 9.999. So if you take the integer of it, it's just 9, which is the last digit, right? It's just 9, which is the last digit. Oops. And 10 to the 0, of course, is 1. So between 0 and 1, if you raise 10 to the power of that, it's going to give you from 1 to 9. And it's going to be a 1 whole digit. Now from 1 to 2, it's going to be 2, right? Because it's going to be from 10 to 100. And so all numbers raised to the power of those numbers from 1 to 2, excluding 2, is going to be always 2 digits used. So you can use this to generalize and to say that you can calculate how many digits you'll require for a particular number. So let's say, and we can do that, of course, with a logarithm. So if we say log base 10, and let's say right now, let's say 100, right? And if we pull out our calculator, this of course is going to be, so let's go, where is log? So log 10, of 100, it's going to be 2, right? Simple. And now here's the thing, we always have to round down here because, so let's say we do log 10 of, let's say 124. It's going to be 2.0 something, right? So we always have to round this down. And of course we also have to add 1 because as we start with 0, we require 1 digit. So then we just add 1 all the time. So we can, so this is essentially kind of an intuitive proof of how if we round, so log with our base, with our number, this is going to be equal, well, of course, well, again, if I do, for example, log base 10, right, of 199, sorry, not 199, log base 10 of 999, it's going to be pretty high up in there, right? So, of course, we have to do this, we have to do this plus 1, we have to round it. We have to round down, we have to floor it, actually, not round it, we have to floor it, but it's the, so if we floor this is always going to give us the number of digits required for that particular number to be done in that particular base. So if you use this for base 2, for example, so let's say, well, sorry, for base 16, our highest possible number, of course, in base our highest possible value in a byte is going to be 255, right? So of course, if we do this, so if we floor it, log base 16 of 255, and then of course we add 1, this is going to give us, and we can do this right now. Oh, can we change bases here? It's a really weird calculator that does not allow that. Or does it allow it? I just don't see it. Where can we put our log base? It doesn't seem like we can. Seriously, TI-86 doesn't have this? Weird. Or maybe I'm just not seeing it. Maybe I'm an idiot, I'm not seeing it, but you know what, let's just use Google for a second. So log base 16. Wait, I was thinking that there would be some. Okay, can I just say, for example, log 16 of 2? I can. Okay, that's great. I can actually no, I can't. Damn it. How do I do this? I thought the calculator would do it, but it doesn't matter. So in Python we can import math, and we can of course do math.log. And if we do math.log, just to show you that it's a thing. So base 16 of 16, this should give us 1, because 16 raised to the power of 1 is 1. So log base 16 of what we were doing before, which was 255 plus 1. And now we need to floor this, by the way. So math.floor this, and this should give us, oops, my bad. Wait. Why? Did I make something wrong here? Wait. Oh, no, I did not. Never mind. I'm an idiot. Of course. Oh, what is log? Okay. Let's yeah. This makes perfect sense, and I'm an idiot. It's wait. So yeah, exactly. Okay. Perfect. Perfect. Okay. So if I do this, for example, this is going to give us 2. Okay, so it's the other way around, I guess. Okay, fair enough. So if we have 255 and 16, yeah, there we go. So plus 1, and we floor this. this makes sense now. I was considering, okay, so what is log? Okay, people are asking what is log, so this gives us 2. This is just like a curiosity thing. It's kind of off the point, but I'll show you what log is pretty simply. So, it's a very basic concept in mathematics. Well, at some point it would be. I'm just trying to figure out how to change template, and it's going to be blank dark. There we go. Okay, so let's say you have a number 2 to the power of 2 equals 4, right? Now, what if you didn't know this? Or let's say to the power of 3 equals 8. You know this, right? Because 2 to the power of 3 is 2 times 2 times 2, which equals 8. Right? Now, let's say you didn't know this. You have 2 to the power of something equals 8. Let's call it x. But you don't know what x is. Now, here you can see that x is 3. But what if you don't know what x is? Well, the response, what x is going to be the logarithm base 2 of 8 equals x. What this means is, so what the logarithm is doing, the logarithm is composed of 2 parts. So it's composed of a base, and it's then composed of your number. And having this is the same thing as saying, b, well, I should, b, well, let's say this equals x. B to the power of x equals n, right? It's the same thing as saying this. So we use it to figure out the answer to these kinds of questions. So if we have, for example, and this is something I can show you in the calculator more easily. So let's say we have 10 to the power of something equals 200. You want to know what x is. Well, you do the logarithm, base 10, so 10 to the power of x is going to be equal to 200, right? And this is just a representation of it. So if you do this, it's going to try to figure out the result of this. It's going to try to figure out what number raised to this base equals this number. So 10 raised to what equals 200. Well, let's pull out our calculator. So we have our log. By the way, the log, when you don't have anything on the base, it's the same thing as saying base 10, right? So that's why here you don't see anything on the base. It's the same thing as saying base 10. So 200, this is 2.3. So this is equal to approximately, let's say, approximately 2.30, right? 2.30. Now, how can we test this? Well, now if we do 10 raised to the power of 2.30, it should be approximately equal to 200, right? Let's test this out. If you do, so 10 to the power of 2.30, 199.52. Yeah, we didn't take all the digits from here. If we had taken all the digits from here, it would be exactly 200. Can you see the where we're getting to right now? So when I do log of something, I'm asking a question. So log b n. I'm just asking a question. What is the number raised to this base that gives this number? Okay, let's look at your example. So your example is we have x to the power of 4 equals 3467. Okay, now this is different because we cannot use the log right now. Why? Because, well, with log, what you're doing is you have a base, right? So x, you have a base. In this case, the base would be x. And you have 3467. So this would be how you'd represent it if you wanted to, right? So what are we doing? So we're doing the base raised to this power equals this, right? And we're now trying to figure out what x is. Now the logarithm, we have to specify a base, so we need to know what x is for here. So we can't do it. Well, what we could use log for is the opposite of this. So if you had, for example, 4 raised to the power of x equals this. And we tried to find what x is. So here we could say, well, log base 4, because 4 raised to something, equals 3467. What is that number? And then you can use log base 4 of this, and your calculator should have a way to switch bases in your log. I cannot find it here. It must have. I'm sorry, it must have. I'm going to try and maybe see if I can somehow. Okay, maybe I should try to wait. How do I? Am I an idiot right now? I am. Well, I don't know. I'll figure it out at some point. But you should have it on your calculator. Oh, so we can't use log to know the x when we only know the raised? No. The way you would figure this out, you don't need log, because you can figure this out in a different way. You can say, well, if you have, okay, let's do this again. It's easier because if you have if you have x raised to the power of 4, well, the answer is x is going to be equal to the 4th square root of 3467, right? And we can compute this too, and I actually have to look up the documentation for it, so math square root docs, Python, square root, wait, I don't want the square root, I want the root, right? But I don't actually need to know this necessarily, because I can just raise it to whatever power I want. But so the number that would be this would be so okay. X is this right is the 4th square root of this number, right? Now a way we can rewrite this is by saying that x equals 3467 raised to 1/4. Right, so if we do that, so if right now we do 3467 raised to 0.25, we're going to get 7.72 something, right? So we can get the x is approximately equal to 7.73, approximately. And you can test this because now, if you do 7, wait, let me, so 7.73, and you can test this because right now if you do, damn it, okay, if you do 7.73 raised to the power of 4, it's going to give us a number that is pretty close to that. But of course, if you use the actual number, it's going to give you way more precise evaluation. So let's use the actual number, and you can see 3567, right? So you can do it like this, and you don't need to go into logarithms, because you can't use the logarithms in this scenario. But are you getting the idea or not really? Got it. Okay, that's good. I had a couple of different ways that in my mind that I thought about to explain this in case you didn't. But okay. So so just to finish up, why was this logarithm important? Well, because now we can ask what the logarithm of any particular base is for a specific number, and we can add 1, and we can floor this. And this is going to be equal to the number of digits needed to represent it. What do I mean? Oh yeah. Okay. Let me just finish this up, and I'll touch on that point. It's interesting to know as well. So, what does this mean that I'm saying right now? What I mean is, so let's say we have 255. It's a number, and this is in decimal, right? So 255 decimal. And we want to know in base 16 how many digits would this take to represent. We can use this. So we can say, we can floor just means to round down, okay? So if you have 2.8, this equals 2. 2.1 equals 2. So we're rounding down. That's what it means to floor. So we're flooring the logarithm of base b, in this case I want base 16, of the number 255, which is in decimal, and then we add 1. By the way, this is one operation, like the logarithm of this, and then we add 1. Or you can floor it and add 1 afterwards. Doesn't matter. So, oh, CMD in the front, sorry. Okay, so so as we do this, so let's do this with our Python. So I'm gonna quit just so I can do this. Okay, so let's import math. So because math is going to be used to floor, so math.floor. So this is going to floor this, and we're going to have math.log of 255 in base 16. Let's just do this. This is 1. But remember, we have a plus 1 here as well. So it's this plus 1, which is 2. This is the number of digits needed to represent this number in base 16. And it's true, because this number is FF. Right, so this is the way you can prove how many digits you can you have to use to represent a particular number in any base. Right, and this is I guess a little side note, because with simple numbers, of course, couldn't be math.ceal instead of adding plus 1? Well, if you seal this, right, okay, of course without the plus 1, this would still be 2, right? But here's your problem. You see the difference? If you seal this, this becomes 2. 256 becomes 2. And why? Because the log of 256 base 16 is exactly 2. Right? So when you're sealing this, it just becomes 2. And you don't add the plus 1. But 256 actually requires 3 digits. As we can see, if we use our original formula, it's going to give us 3. It requires 3 digits, because obviously it's after FF, right? And FF is the last digit of base 16. So 0FF. After this, you have 100. You have 3 digits. So the math.ceal doesn't work when you have integer numbers as results of the log. The reason we do the floor is because we don't actually have to necessarily floor this, but I mean, we obviously we do have to floor this to get the result we want, but yeah, but that's why the sealing doesn't work. The seal always works if your numbers are not integers as a result. Why? Because if your number is not an integer, so let's say it's a 0.9. So let's say that the result is 0.9, right? It's going to seal this into 1, and that would be the result, because the floor of this would be 0 plus 1 in the original formula. But if the result is 1, the ceiling is still 1, but the result in the previous formula, the floor would be 1, so the result would be 2. So there would be a discrepancy, right? And I should have explained this in a better way. Let me just do this in this way. So let me do it with this. It's easier. So let's do math dot actually let's just do a math.log, and let's do 256. Sorry, let's do a different number. Let's do 10. Sorry, not 10. Let's do 9, but in base 10, right? And we all know that the number 9 in base 10 requires only one digit. The result of this is 0.9, 0.95. If you floor this, it's going to be equal to 0. If you seal this, it's going to be equal to 1. Now, if you proceed to flooring this, you have to add 1, which is going to be equal to 1 at the end. So these two values are the same. But if we go for the number 10, which we know requires 2 digits, right? It's the number 10. The result is going to be exactly 1. If the result is exactly, if the result is exactly 1, if we floor it, or if we seal it, this will be 1, right? But when we floor it, we also have to add 1, so this becomes 2, right? But this is still 1. So it's the wrong number, you know what I mean? And that's the reason why we have to floor it and add 1 instead of just sealing it. Yeah, you're probably never going to have to use this, but it's a nice thing to know. Because even if you cannot immediately calculate what number would a particular number be in a different base, you can at least know how many digits you'd need. And for bytes, you can use from 00 to FF in hexadecimal, and this will represent all 256 possibilities of bytes. And of course, you can also think of a byte. So if a byte is 7 digits, if a byte is 8 binary digits, so 8 bits, and bits are only 0 or 1, so there are only 2 possible digits. The whole possible space of a byte has to be 2 to the power of 8, right? Which is exactly 256. So another way to think about it. Oh, thank you for following Nightcall-X. Really appreciate it. So yeah, so this is base. These are bases, and they're pretty important as well. But there's not much more to this. I may have expanded a bit more into this than is needed. You don't really need to know that much about bases to successfully use them in everyday operations. So the only thing left is virtual environments. And and by the way, how much bytes is in FF? Yeah, that's okay. So sorry, I don't need the board for that. I can use Python. So so you can type it like this, and you can have 255. But here's the thing. So how many bytes is in FF? That's a great question. Well, FF is a 255, which is if you do in binary, if we do it in binary, it would be a series of 8 ones, right? So 8 digits, 1, right? So this is still 1 byte. And so in FF, there's still 1 byte, right? So let's say, because of the definition of byte, a byte is 8 bits, right? And a bit can be 1, and a bit can be 1 or 0. So this is a byte, right? But this is also a byte. This is also a byte. Well, to be fair, fine. If we include all the 8 possible digits, like this is a byte, right? This is a byte. This is a byte. This is a byte. It just so happens this is the last, is the highest byte, I guess, right? You ask for bytes? Yeah, right? So when you have, for example, let's say you have, yeah, exactly. So FF, so if FF represents a byte, FF represents 2 bytes, so 3 bytes and 4 bytes, and so on, right? But again, it doesn't have to be FF. If we're always doing it in base 16, so 0xFF, this, 0xFF is still 1 byte, right? FF is another byte. So 2 bytes. 3, 4, right? You can have, say, FF0E, right? We still have we still have 2, etc. Uh, and yeah, of course, and yeah, if you do FF, you have in here and 1 byte. If you do FFFF, you have 16 bits. So think of it in this way. Let's say, so this, yeah. So, okay. Wait, this is not what I meant. I meant this. There we go. So, wait, do we have the opposite? We do. Okay. So, for example, okay, F5, right? F5 is this. If you notice, this is 1, 2, 3, 4, 5, 6, 7, 8. Now, let's say F5, and then we have CD. It's another byte, right? You'll notice now, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. So we have 16 bits in total, and a byte is 8 bits, so we have 2 bytes, right? So if you keep adding things, so you have E5, you're going to have another sequence of 8 bytes in front of it, of 8 bits in front of it, so it's 3 bytes, and we have BD, it's 4 bytes now, right? So it's if you put them together, it's still going to be different bytes, because all you need to represent a single byte is two hexadecimal digits, and this is why hexadecimal becomes really useful when correlating it to bytes, because it's really simple. 1 hexadecimal can be used to represent 4 bits, right? So this we have 4 bits. So if you have right, so 0f, you can still have a byte if you pre-appended everything with zeros, right? So if you do, for example, bin 0x 0f, you have 1111, which is 4 bits, right? But the maximum possible representation of 2 characters is a byte. But sure, if you have 0xf, right, you can say that this is not a byte, it's half a byte, right? But surely if you do this, it's not pre-appending it, right? But again, if you do hex of 0b, oops, this, it's still going to be 0xf, and this is a byte technically, right? It just has zeros there. But yeah, hopefully that was understood. So let's jump into virtual environments here for a second. It's a different topic. It's a lot more simple. So what are virtual environments? And this is going to be pretty quick introduction to this. So let's open up our PowerShell window here. Let's put it right here. Now you'll notice that in here, so ls, let's go into ransomware just because. Actually, let's not. Let's create a new directory called, I don't know, project 2. It doesn't matter. I'm going to delete it at some point. It's just, for example, call it project 32. Okay. We have nothing inside of here. And you see this base in here? You'll probably not have this. This is because of my Conda environment. But let's assume we don't have it. Right, we don't have it. This is here just because of my PowerShell profile. Don't mind it. Now, we have a Python installation, right? And if you click Python, you go into your shell, you have your Python installation. Now, when you install modules in Python, and again, what are modules? Modules are simply if you go into there we go. So if you search, for example, I don't know, what's an example of a module? So for example, time module, Python. So it's simply going to be a library you can call up from, and I'll show you in code. It's easier actually. So if you have, let's say we have this test.py file, right? But we also have another one called, so we're just going to have a folder actually. We're going to call this underscore modules. And inside of here, we're going to have our supermodule.py, right? And in here, we're going to have a function that's going to do print stuff, and this function is just going to print hello world, right? It doesn't matter, hello world, right? And it's in a different file. And right now, we are, let's go into our shell, and let's actually go into our initial project. So we have our test.py, we have our text, doesn't matter, we have our modules. So when we go into our modules folder, when we go into our modules folder, we're going to have our supermodule Python file with functions. Now, what you can do is you can have a lot of functions in this file, and you can call them in your main file. How do you do this? Well, first of all, you have to tell, you have to add a special file inside this folder to tell Python that it's going to be called. So that it can be called in as a module. And you add something called underscore init __.py. You don't have to put anything in this file, it just has to exist. Now, what you can do is you can do from modules import our super module. And notice how it auto-completes already. Now, if we just do this and we run our file, nothing's going to happen, right? But here's the thing. When we do this, it's going to go into a folder called modules, right here, and it's going to go and look for our super module, which is here. And it's going to basically run what's in here. Right? So right now we have our, so it's going to go into here and it's going to just run this definition of the function. So in your main file, you have now ran the definition of this function. Now to make sure the code doesn't break, so if you have different functions with different names from different modules, you have to refer to this as supermodule dot something. In this case, it auto-completes with print stuff. That's the only function that exists. And now you can actually call this function. So you can come up over here, play it, hello world. There we go. Now to prove to you that this actually runs instead of something else, you can actually just put print hello world, and without calling anything, if you just import the module, you're going to see that it's going to run the code and it's going to print hello world. Right? It's going to go into here and run this code. Why is this really useful? This is useful because, of course, you can download from the internet or even have a bunch of modules that you created yourself and a very simple file that calls modules from this. So you can have like auxiliary modules separated neatly into different files that then you call upon in your main file and you call some functions from it. So it organizes your code better. And I use this from because you can use this, so if you have a folder, so you can do this, or if you want to import particular functions, you can as well. So you use the dot as I used before. So from modules.supermodule, you can also import the only function that exists actually now, which is called print stuff. And right now we only have the print stuff. We don't have anything of supermodule. The only thing we have is print stuff because that's the only thing we imported. So if we run this, it's going to print hello world anyway, right? And if you didn't have a folder, or if you just had a file and you wanted to import that whole file, you can just forget the from and use import, right? So if you have, for example, let's say supermodule is right here, and let's delete the modules folder. let's delete the definition of this function. Now, if you do this, however, it's going to locate your supermodule, and it will run that code. As you can see, it printed hello world. Did you create that modules and init manually, etc.? Okay, so this is this PyCache is completely automatic. You don't actually need this right now. The init is needed if you have, for example, a folder, which is going to be considered kind of like a package. So let's say you have a folder called modules, and this is just to organize your code. So all your modules go here, and then you can put your supermodule. When you do this, you can say from modules import supermodule, right? You can still say this, and it will run. But you should always create your init file manually yourself. So underscore init __.py, because this is basically going to help Python understand where the top level is going to be. And you'll get this maybe later on, but you should always create this, okay? Even though you can technically call it without it, when things get more complex, it will be useful to have it. And also you can write code in here. This code is basically going to be executed every time that anything from inside this modules is going to be called. But we'll get into that later. The idea right now is just to show you that you can import other files, Python files, that have functions in them. And those functions can import other things too. And importing just really means that it's going to fetch that file and run that code, essentially, right? And why is this important? Well, it's important because it allows you to use a lot of the functionality in the system. So for example, when we used, I don't have it already anymore, do I? When we went through input and output, there we go, we did. When we went through input and output, we actually used an import. We imported IO. And IO just happens to be a standard library in Python. So it comes included with the Python installation. So you don't have to install anything. So you just import it. And when you import it, you have all the access of all of the functions and classes and objects inside of this IO. If you have another directory inside modules, like modules test supermodule.py. Okay, so let's do that for a second. Let's create another directory here saying supermodules, and inside supermodules we have a module. We have our supermodule. Now, yeah, supermodule still the same. Now, let's actually comment this out instead of deleting it because we're going to be using it later. So we can do, so if we say from modules dot supermodules import supermodule, it's still the same thing, and you can use it and it will print hello world. Okay? Now, yeah, that's basically it. Now, for example, if you do from modules import supermodules, this is wait, let me delete this because it's confusing. This is not going to give you an error, right? And we'll get at it in a bit, but that's because, again, and this is where this comes into play as well, because you notice as soon as I import the folder, not the module, and when I import the folder, the init gets executed, but not this. Okay, we didn't import this, we just imported the folder. The init gets executed, right? And when we do what we did before, in here, the init gets executed too, but we also imported this, so this gets executed as well, right? And this is, and you can access anything inside of supermodule by just saying supermodule dot whatever function is inside of it, right? But yeah, and this is what we're doing when we're doing the I/O. So when we did the I/O part, we imported I/O, which is a Python file somewhere, io.py, and it has a bunch of functions inside of it, and classes as well. You can see this is a class. We'll get into that later, but you can just use them by saying io dot whatever's inside of it, and you can see a lot of different things in here. So for example, open. Where's open? Open is a function, or let's say open code, right? Open code is a function. We can access it by using io dot something, and this is what we used before as well. Something also important, for example, you can import time, and time has a bunch of things. So you can do time.sleep to make your program just sleep for, or do nothing for, do nothing for X amount of time, and we can also do time dot. Actually, we shouldn't do this. We can tell what time it is right now, how much time has passed. We can do all sorts of things, and this becomes really useful. Hey, hello there, Wolf. And this becomes really useful when you can later on download packages from the internet. And how do you do this? Well, let's say you want to download. Oh God. So requests PyPy. Okay. There we go. For example, this is a module in Python, but it doesn't come installed with Python. So for example, if I go into our Python interactive shell and I type import requests, it's going to say no module named requests. We don't have requests. It's not in the standard library. But we can install it with pip. Pip comes with your Python installation, and you can use pip to install things. So if you do pip install requests, it's going to install the requests module, which then is going to allow you to just use import request on your Python. But here's the thing. What if, so you have a project and you require particular modules, or you created your own modules, or whatever happened. You have 30 different modules that you have to install in specific versions. Right? And then you have a different project that requires a different version of modules. Then you have to uninstall the modules you had before, reinstall like the different versions, or downgrade or upgrade. It becomes very messy. And that's where virtual environments comes into play. A virtual environment is basically just a contained Python installation. So how do you create a virtual environment? So right now, my Python is the normal Python, right? To create a virtual environment is really easy. You use Python and then -m. -m means you're invoking a module, essentially. So -m venv, which is the name of the virtual environment module you're invoking. And then you just type the name of the module you want. So let's say right now I want ransom. There are other options, and you can look this up, but this is the basic idea. That now it's going to create a virtual environment. And it's done. How can we tell it created a virtual environment? Well, if we look at the files, we now have another folder called ransom. Right? Now, if we explore this folder, what does this folder have? So input-output, ransom. So if we explore this folder, we notice that this folder has a script. It has a pyan configuration file, so it's a configuration for the environment. Oh damn it! It's on the other side. So you can see here, it's just a configuration for it. The version of Python is here. The place where the Python installation is. Then you have your scripts, and then you have a lot of stuff. So you have pip, you have Python, which is the Python for this environment, this contained Python installation. Then you have a couple activate things, and this activate things are for Python activation. What does that mean? Well, right now, even though we created our virtual environment, we're not in it, right? We're not in this virtual environment. How can we get and work on this virtual environment? We can just use the command source, and then we go inside of our folder. In this case, it's called ransom, and it's in ransom bin. Wait, is it not? Oh, it's Windows. It's in ransom scripts activate. Or, sorry, activate.ps1 because we're in PowerShell. Oh, we don't need the source. I'm an idiot. Damn. Yeah, this is not Linux. So ransom scripts activate.ps1. That's all you need. Okay. And when you do this, you notice that there's something that shows up here in parentheses. This is your active environment. Now you're in this environment. Now, if you use Python, you're not using your normal Python. You're using your virtual environment Python. So this is a contained Python installation. So if I do import request, for example, which is a module, it doesn't exist. But let's install this. So let's do pip install requests. Oops. We're inside Python. I'm an idiot. So let's do pip install requests. Right, so it's going to collect the request, and then it's going to install it. There we go, it's installed. Now if I do Python again, and I do import requests, no error. We have successfully installed it in our contained environment. Now what happens if I go out of this environment? How do I exit my environment? You can just do deactivate, and it's gone. No more ransom in parentheses, it's gone. No more environments. Now, if you go into your Python installation and you click, you try to import requests, it's not going to work. It's going to tell you module not found because you have not installed requests on your main installation of Python. You only installed it in the virtual environment called ransom. Anytime you want to activate it again, just go into the directory ransom scripts activate.ps1. There we are. And every time you execute something, you're going to have it again, right? No error, right? And this is really useful to do with projects. So every time you have a new project, you should create a virtual environment for that project. If you're going to, mess with a lot of the modules that you can get, you can install a lot of modules, and that way you don't touch your main Python installation. You're just working with a contained Python installation. If you want to completely destroy it, you can. The way to do it is you just delete the folder. That's it, right? That's all you need to do. So deactivate. If you're on Linux, by the way, you would do it. You can do it in the exact same way, except to activate your environment. Instead of going to ransom scripts activate.ps1, and again, if you're in command prompt, so let's open up command prompt. In command prompt, right? Instead of PowerShell, you wouldn't use the PS1, right? You would use where am I? Oh god, I hate CMD. Okay, so you wouldn't use wait, don't we have a script there? Am I tripping right now? Ransom. Oh no. Well, yeah. What is in here? Yeah, we have a scripts directory. What the hell's going on? So wait, ransom scripts. There we go. Activate, and you would do the activate.bat, right? And then you see the ransom here. And then the deactivate is the same. Now, the reason you do the bat is because obviously if you do the PS1, it's a PowerShell script, so it's not going to interpret it as a PowerShell script because you're in command prompt. So it interprets as the batch, right? And if you're in PowerShell, of course, you use your PS1 because that's for PowerShell. Now, if you're on Linux, you do it differently, but it's very similar. But if you're on Linux, you're going to do source, and then your folder ransom, and then there's going to be a folder called bin, and then it's going to be activate, and that's it. And then you click, and you're good. That's on Linux. How can I show you quickly right now? I can show you this, I guess. So let's open up a connection to, let's say, I should have some Linux under like super handy, but I don't have it up right now. We can do this, it's easy anyway. So SSL, DNS, let's look up this one. So let's go for here. Here, I guess. Let's log in. Okie dokie. So let's say we have, so this is Linux that we are in right now. Let's make a directory, tests. Let's change to that directory. And right here, we want our virtual environment. And I'm going to deactivate our Conda environment because it's just going to be better. Anyway. Okay. So, in here what we're going to have is, can I make this bigger? I shouldn't. It doesn't matter. Okay, so let's create our environment, right? So if you have Python, there's no Python, but there's a Python 3. There we go. So we do a Python 3 venv myenv. Doesn't matter what the environment is called. Oh shit, this doesn't exist. Okay, so yeah, you have to also install this, by the way. This is pretty important too, obviously. But that's the thing. As soon as you do it, it will tell you, which is not a big deal. And now as soon as you do that, it will just work. Let's go. There we go. And now when you see you have your directory here, so now if you do source myenv bin activate, there you go. You have your parentheses here, all is good. And your Python installation is in your virtual environment, and we can always deactivate it like this. So that's how you do it. So Linux, Python, so Windows and Linux. So that's it. That's virtual environments. And that's all for today. Are there any questions right now? I know that today was quite a bit of information. Maybe it was a bit confusing. But hopefully if you guys have any questions, I would appreciate it if you guys can tell me now. And if you guys rewatch this later, just put a comment with your question or doubt, and I can clear it up. The document that I'm going to write for these lessons and in next week as well. Any questions right now? And thank you so much for watching so far. Really appreciate it. And right now I'm going to take a look at any particular events that have happened because I wanted to pay attention to chat. So nothing particularly interesting, I believe. Thank you so much for the subscriptions, by the way, guys. Really appreciate it. Is it okay if I message you on Discord if I'm stuck with something? Sure. Anyone, if you are stuck with anything or have any doubts, just go over to our Discord. You can message me. You can message anyone else. So for example, if you go into our website, so whitehathacking.tech, just click on community, right? And you'll go into our Discord server. You can join it. And when you are there, right here, I have a mention. So you can ask anything, for example, in coding channel, you can ask anything here. You can ask me too. You can just DM me with any question you want. It's totally fine. I answer every single question. Sometimes I do take some time, but I answer every single question. We also have a giveaway, by the way, in which you just have to react to enter. And in this giveaway, you can win a 1 month Nitro. And yeah. Any other question right now? We have some new designs coming up as well, by the way, and because these are really cool. Like I'm wearing that shirt right now. This shirt is actually really nice. Only thing that I recommend with this with everything in here actually, um, if you um, if you're not really familiar with things that are, for example, 100% ring spun cotton, you should try to, like, if you're an L, for example, you should order like an XL, because when you wash this, it might shrink a little bit. So, just keep that in mind. But everything else, like, really awesome. Had no problems with the shipping at all. I had problems with a lot of other things in shipping, but no problems with this. Okay, I will end this in about 4 minutes. Why don't you have a sub button? Well, I started streaming actually pretty recently, and on this account, it's a new account, ish. Um, and on this account, I haven't streamed enough hours for the subscribe button to appear. I believe it's 50 hours. I'm not sure. I believe it's 50 hours until the subscribe button appears. So hopefully we'll do soon, because I think that I have streamed for quite a bit of hours, but not that many actually. So if I go look, because on my YouTube channel, so let's go look in here. So my videos, actually not the videos, I wanted my live streams. So past live streams. So we did, so 2, 3, so 4, 5. Yeah, actually we're quite a bit away from the 50 hours. I think it's 50 hours. We did one more. I'm looking on. Yeah, I should be looking on Twitch, not on YouTube. But since these are uploaded anyway, right? But they missed quite a few hours, I believe. So if I go into my channels here, and I go into wherever it is, do I not know where this is? Do I just click on here? Yeah, videos. So past broadcasts. We only have like the recent more. Okay, so we only have the more recent ones anyway. Um, so 5 and 6. There are no more. There are no more, I guess, in here. But but yeah, I think it's the 50-hour thing. Um, I can just Google that really quickly. Twitch affiliate. Oh, it's not. I'm wrong. I'm wrong. I'm sorry. I'm wrong. I have no idea why I thought 50 hours. It's 50 followers. Um, and over the last 30 days, 500 total minutes, 7 unique broadcast days, and an average 3 or more concurrent viewers. So this is the criteria. So hopefully at some point, not in too long, we will have a subscribe button. You only streaming on YouTube? No, Simstar. I'm actually streaming on Twitch as well. So I stream on YouTube because, well, I stream on YouTube because I'm multi-streaming, right? So I'm streaming on YouTube and on Twitch at the same time. To be honest, I pay a bit more attention to Twitch because it's easier for me to control and see. But I see chat for both YouTube and Twitch as well. I'm not incredibly active on YouTube per se, as I am on Twitch. Although it's, in terms of live streaming, it should be pretty much the same thing. And everything goes to YouTube regardless. So all of my live streams go to YouTube regardless. Although I try to kind of cut them down a little bit, but yeah. Okay, I guess that's it. So it's 7 right now for me, and I will go now. I think that I answered all of your questions. If I didn't, just DM me. It's the easiest thing. Just DM me, or post as a comment on YouTube. I read everything, so I read all the comments, all the messages. So whichever social platform you come, I'll read it. Thank you for being here. Oh, you're welcome, guys, and thank you so much for being here and for supporting the stream. Really appreciate it, and I hope you guys found this insightful. I haven't yet actually uploaded the documents for the lessons on the website because I was waiting for this so that I could actually start with these basics before the ransomware project on the website. I think it would be better, and I kind of wanted to see if you guys had any questions afterwards as well, so that I can explain this a lot better in text, because it's easier to explain things in text than it is in a live format. But I hope this was incredibly useful, or I hope this was useful for you. Anyway, see you guys. I hope you've had a nice Christmas, and we'll definitely see each other. Oh, we're not gonna see each other. Well, I'm not gonna live stream before um, uh, New Year's. So happy New Year's as well, guys. And as always,